The production of synthetic emeralds. Synthetic and imitation stones are artificial products which imitate a stone that occurs naturally. Whereas imitation only resembles a natural stone by its appearance, green glass for emerald, a synthetic crystal is in many aspects identical to its natural counterpart. The chemical composition as well as the crystal structure, therefore all physical constants such as the refractive indices, density, hardness, cause of color, etc., must correspond with the natural counterpart. Only under these conditions, an artificially produced crystal may be called a synthetic. The production of the synthetic emeralds has been performed for a long time with a variable success. In 1848, Abelman was able to produce some of the first crystals. Before World War I, in Germany, experimented growth with synthetic crystal and developed the fundamental technology for the production. The first commercially relevant results were scored by Carroll Chatham in USA, Gilson in France in the 60s. The crystal growth technology that they used was based on a melt of raw materials as oxides to which chromium was added. Usually, the melt is kept at a temperature of approximately 800 Celsius under normal pressure in a crucible and of precious metal. As soon as the melt is oversaturated, crystallization may start with the formation of spontaneous nucleation. This gem growing until they are numerous enough to form crystal clusters. Thus, the reconsolidated material develops into a magnitude of small intergrowth crystals. Spontaneous nucleation may be inhibited by installing a slice of beryl as a pattern for the grown crystal, which continuously grows as long as the all dissolved material is attracted to the beryl plate and forms one single crystal. This is an optimal result for crystal to be used as melt is oversaturated. Through this process, a gem, the environment of the formation of these synthetics, but the flux method differs sharply from the environment in which natural emeralds is formed. Notably, by the lack of water. That is why such products, like synthetic emeralds from Chatham and Gilson, usually are rather easy to differentiate from natural emeralds. Gemologists may recognize veil-like residual flux droplets in tiny voids during a microscopical inspection. Nowadays, flux synthetic emeralds are mainly produced in the USA, in Chatham, in Japan, in Amori, and in Russia. The production of Gilson, formerly the most important producer in Europe, has moved to Far East due to the selling of the license. Hydrothermal synthetic emeralds, the first step to produce synthetic emeralds by the hydrothermal method, were made at the beginning of the 60s. In case of the hydrothermal process, the crystals do not grow in the melt, but in overheated water. The raw materials oxidize or beryl together with additional chromium and dissolve in an autoclave. An autoclave is comparable to a pressure cooker. In order to raise the solubility of the raw material, the acting aqueous solution has to be extremely acid. Under the influence of heat, 550 Celsius, and pressure, 1000 bar, and steam, the primary materials are dissolved so that the autoclave itself doesn't start to dissolve. A lining made of precious metals, silver, gold, and platinum is required. Furthermore, it is important that within the autoclave there is a temperature gradient, a difference in temperature of about 60 Celsius. In the hottest zone, under saturation, the substances are dissolved. In the cooler zone, over saturation, the chemical elements are deposited on the exposed seed plate by means of the vapor. The chemical components move atom per atom to the seed plate, which grows. Synthetic emeralds are formed through this procedure. Johann Lechleiter was the first who succeeded in growing synthetic emeralds on a faceted, colorless beryl. Later on, Linde, USA, produced larger synthetic emeralds by the hydrothermal method. Those contain a seed plate of natural, colorless beryl. Hydrothermal synthetic emeralds, which have been produced since the 60s, have considerably increased in quality. Originally, only a growth rate of a few millimeters was possible during each run of hydrothermal growth or per autoclave filling. Thus, the crystal or seed plate had to be covered many times until the coating was sufficiently thick. The first multi-layer synthetic emeralds were called sandwiches. Samples from this older type of hydrothermal emeralds usually exhibited a multitude of inclusions, most of them consisting of tiny penakite clusters and acidic voids with a liquid and gas filling. Hydrothermal synthetic emeralds are today produced by Regency, formerly the USA, Vesa, Russia, Kimberley, Barron, Australia. Kimberley hydrothermal synthetic emeralds. Mr. Arthur Birkner, the producer of Barron hydrothermal synthetic emeralds, in front of a small and modern factory in Perth. Geological maps, mineral samples, bookshelves, and a desk covered with analytical printouts, notes, and diagrams fill in the office of the successful producer. The 80 years of costly development, of which the final result were these most impressive crystals that are the horror for many gemologists. Mr. Birkner told that his aim was not to fake real emeralds. What he really wanted was to produce stones which come as close as possible to the natural counterparts. Thus, people who are fascinated by emeralds are now able to afford a piece of jewelry which the stones may be even more beautiful and durable than natural emeralds. For reasonable price, of course. It seems that the market of synthetic emeralds is nearly detached from the market of natural ones. There are numerous steps which are necessary for the successful production of synthetic stones. Beryl mine scrap from Brazil, which are used as raw material, chopping the beads and selecting the usable parts, which are used as charge for the autoclave. Thus, natural beryl is used to produce synthetic emerald, making cylindric capsules out of gold plate to furnish the inner lining of the reaction volume in the autoclave, offering a space of approximately 4 cm in diameter and 30 cm in length. The electric furnace is equipped with special ceramic parts, which they also produce in a neighboring workshop. In another room, the seed plates are cut out of the finished synthetic emerald crystals. They are cut flat and used again in a forming process. These seed plates consist of slides of beryl crystals, cut approximately 30 degrees obliquely of the C-axis. On the surface, the crystal growth proceeds the most rapidly. At any one time, 6 seed plates go into one gold capsule, where they are suspended on platinum wire. The composition of the hydrothermal brine and the combination of the added coloring trace elements like chromium, vanadium, iron remain manufacturer's secret. An explosion-secured room with at least 100 furnaces which hid the autoclaves. Important steel rods were ready to hold and withstand the extreme pressure in the autoclave during the synthesis. Heat and pressure are controlled by computers. It was obvious how capital-intense the production of high-quality synthetic emerald is. How carefully the finished stones were cut. They are on stock in different shades, shapes, and cutting styles. Barron synthetic pink beryl, new synthetic beryls, which he grew the same hydrothermal way as the Kimberley synthetic emeralds. Natural pink beryl is usually named morganite. It owes its rose color to trace of manganese. The crystal lattice of beryl allows manganese in 2 different valence states. The trivellation has a strong coloring effect. A well-known example are the red beryls from Wahwah Mountains in Utah, USA. The bivalentation has a weaker effect on manganese, so morganites with manganese 2 mostly exhibit a pink coloration. On the other hand, it is surprising that the new synthetic pink beryls of Barron do not show any traces of manganese, but have remarkable traces of titanium, which seems to cause the pink color. This type of coloring is not known among the natural pink beryls, since the synthetic pink beryls are produced following the same process as the synthetic emeralds.